So this is question 7 for the experts, and the circuits of figure 7 are slightly more subtle in their behaviour than those of figure 6. Each circuit is driven by a 0 volt to 10 volt input pulse of 100 microseconds duration and uses diodes that can be assumed to be ideal. For figure 7a, sketch the response of VO and IC to the input pulse. So figure 7a looks like this. And we've got 22 nanofarads here, 1 kilo ohm, whole one, let's see, that's D, this is R2, and it's 1K as well. Okay, righty then, so looking at the circuit, we can have a crack at the graph. And V in will be in blue, V out will be in green, and IC will be in red. Okay, so our input pulse looks like this. And it's 10 volts. So when the pulse is applied to the circuit, the diode will conduct immediately and the capacitor will charge up to some value that we're not sure about yet, and some current will flow through R2 as well. But the diode will conduct for the whole of the pulse. It will conduct a current, even if it finishes charging the capacitor, it will still conduct a current through R2. So we can say right off that the output voltage will go up here and will stay up all the way along, and then something else will happen. And that's something else that's the interesting bit. So by the time this pulse has happened, because it's 100 microseconds in length, this is 0. The C has been charging up throughout the pulse length, and we can work out what the time constant is. We can have tau is equal to C times R1, which is 22 times 10 raised minus 9 times 1 kilo ohm, or 1 times 10 raised 3, which is 22, and 9 becomes 6, times 10 raised minus 6 seconds, which is 22 microseconds. So 22 microseconds for the charging time constant. So our current waveform is going to go up to some value that we haven't decided about yet, and then in time constant of 22 microseconds, so it's approximately 4 time constants, or 4 and a bit. So it's very, very nearly all the way down, pretty much. So the capacitor would have charged up to 10 volts in that time, would charge up to the input peak value. Now, as soon as we remove the pulse, the diode will stop conducting, and the output voltage will be derived from whatever C is charged up to, and half of the voltage that's on C will end up across V out, and half of it will end up across here. The only problem is, of course, that 10 volts looking this way ought to produce 10 volts looking that way. So actually we'll expect a drop from here downwards by half of the value that C is charged up to. So the very next thing that happens is this will drop down to 5 volts. So we end up with 5 across there and 5 across there. This bit may as well not be there anymore. And we can take that off as well. But there's no point in replacing this with a short circuit because this diode will not conduct anyway. So this bit of the circuit just doesn't exist anymore. And we can say what the time constant will be in that situation. And there will be, I mean, this capacitor will now release it, or give its energy up to the 2 resistors, and as this capacitor discharges there will be an exponential decay like that, and these 2 resistors now appear in series from the point of view of the capacitor. There's a loop. Now that the capacitor is the energy storage medium, it's driving the circuit, the IC has changed direction, and as far as this loop current here is concerned, these 2 resistors appear in series, so the time constant for the discharging part of things will be, so I'll call that 1, tau 2 will be C times R1 plus R2, which is 22 nanofarads times, well, it's 2 kiloohms, so that's 44 microseconds. Using the same logic as here. I mean, that's now 2. So we've got a time constant for this bit of 22 microseconds and a time constant for this bit of 44 microseconds. And the capacitor current in this time period is doing this. And the peak value is going to be, well, it's 10, if we can write it out actually, I is V upon R, and it's 10 upon the 2 kiloohms, so it's R1 plus R2, which is 5 milliamps. That's 10 over 2K is 5 milliamps. So this should be 5 milliamps. Oh, we never did the peak current for that one as well either, did we? It will be, peak current in the capacitor is 10 volts divided by 1 kiloohm. So this is going to be, I is V upon R, so it's 10 divided by 1K, which is 10 milliamps. Alright. Yeah, 10 milliamps. So that one's here. That's milli. Right then. So, question 7, part B. We have the circuits in figure 7 are slightly more subtle than the behaviour of those in figure 6. Each circuit is driven by a 0 volt to 10 volt input pulse of 100 microseconds duration and uses diodes that can be assumed to be ideal. For figures 7b and 7c, sketch the response of VO to the input pulse. So we only need VO now, and we'll have the output, and there's a diode and a resistor, and the other bit of the output, and in parallel with that there's a resistor, and there's a capacitor, and the source. So we've got 15k and 15 nanofarads, and D and 2K. And this is R2 and this is R1 and this is V out. So we will be drawing the graph. And V out will be in blue. I'm sorry, V in will be in blue. And I can draw V in now actually. Something like that. And this will be 0 seconds and this will be 100 microseconds. And this will be 10 volts. V out will be in green. And if we choose to draw IC, it will be in red. Okay, so this is the first circuit on this tutorial sheet, which is actually high pass. So we've got the capacitors now in series instead of in parallel with the output voltage. So initially, as the pulse reaches the right hand plate of the capacitor, it will pass through, and the voltage V out will suddenly jump to 10 volts. So we'll have a sudden. If you think about a standard high pass network, its output voltage with time is like that for an input that was like that. So that's where that's appeared from. And then as soon as that happens, we'll end up with the 10 volts on here, and that means that there'll be some current in R1, which is fine, and also the diode will be in conduction. If we assume initially the diode isn't in conduction, 10 volts here, if it's not conducting, there's no current in R2, so there's no voltage across R2, so all of the 10 volts falls across the diode, therefore it conducts. So the diode is going to be conducting. So we'll have R1 and R2 essentially appear in parallel because there is no voltage across the diode when it's conducting. So we've got the output voltage will fall back to 0, and it will do so with the time constant, which is tau 1, and it will be C in, times R1 in parallel with R2, which will be 15 nanofarads times 10 raised minus 9 times 15k times 10 raised 3 times 2 times 10 raised 3 over 15 times 10 raised 3 plus 2 times 10 raised 3, which is 15 times 2 over 15 plus 2, 1.76 times 1000 times 15e minus 9. So that's 26.47 microseconds. 26.471 microseconds. So in 100 microseconds we'll get about 4 time constants. So it won't quite make it all the way, but it will have a fair try. So something like that, I would think. Maybe even more. And then there will be the question of, let's see if we're in the answer we give, do we assume? In the answer we give, we assume it basically gets to minus 10 volts, which is more or less true. To avoid making the question too difficult, we'll assume that means pretty much all the way. Right then, so we have now a situation where the trailing edge is going to go into the circuit, and that means that for a short period of time at least, there will be a sudden decrease in output voltage, and then it will return to zero after some future time. And the time constant with which it does that, so this is T1, or tau 1, sorry, and this is tau 2, and tau 2 will be C times R1. And the reason is, with the pulse going, with the falling edge of the pulse passing into the circuit, we're now in a situation where this is suddenly dropping from 0 to -10, because what's happened is during this length of pulse, we've charged up this capacitor to 10 volts, and what we're then doing is saying, alright, well we've got 10 here and that's 0, but if I suddenly drop this by 10 volts to 0, unless I'm going to do some work to this capacitor, that's to say put some charge in or take some charge out, instantly, which isn't allowed because you'd need an infinite amount of current to do that, if this side drops by 10 volts, this side has to drop by 10 volts as well. Now that's not to say the capacitor has no voltage on it, it's to say that this has to become -10. So if that's -10, then the diode is biased in that direction, where we've got, assuming it's switched off, we've got 0 on this side because there's no current flow, because we just assumed the diode switched off, and we've got -10 up here, so it's reverse biased by -10 volts, no danger of conduction. This branch, nothing to do with anything anymore, and we're down to a regular high pass RC network of 15 nanofarads and 15 kiloohms. So we'll have tau 2 is 15 nanofarads times 10 raised to -9 times 15 kiloohms 10 raised to 3. What's 15 times 15? Don't know the answer to that. 15 E minus 9 times 15 E3, 225 microseconds. So this is an extremely long time constant actually. It doesn't give you nowhere even close to how I've drawn it. It's sort of much more like that, but we'll ignore that for now and assume it's right. So if this makes it all the way to 0 in the charging up period, then we can call that -10. If we want to be honest with ourselves and say, okay, it doesn't quite make it, it gets to like here, we have to work out what this voltage is by the usual methods. That's to say, you do V out is equal to VA, and VA would be 10 volts in this case. I'm sorry, it's the other equation, isn't it? Yeah, e to the minus t upon tau, and you sub in the time. So we do VO is equal to 10 e to the minus 100 microseconds over 26.471 microseconds, all in brackets. And that would give us minus 100 divided by 26.471 is minus 3.77, so e raised to that is 0.022 times 10, so we get 0.228 volts. So this is not quite 0, it's actually 0.228. So secretly this would fall to not minus 10 but minus 9.782, is it? No, not right. 772 maybe. 10 minus 0.228. 9772. Can't have two 2s there and one yields a 7 and one yields an 8, that's just not right. 772. It doesn't affect the time constants, it just depends how you want to answer the question. Looking at the solution that we gave in the sheet, we haven't worried too much about this slight inconsistency, so I won't worry about it if you don't. The only important thing to note is that the diode here is such that the time constant of T1 and T2 is different. Alrighty, so that's 7b. So this is question 7, part C, and the question says, the circuits of figure 7 are slightly more subtle in their behaviour than those of figure 6. Each circuit is driven by a 0 volt to 10 volt input pulse of 100 microseconds duration and uses diodes that can be assumed to be ideal. For figure 7c, calculate the time for which VO is below 2.5 volts after the falling edge of the input pulse. So, question 7c looks like this. We've got an output and diode and a resistor, and this is the out, and then we've got a resistor and a battery, and this is all in series with a capacitor, and that's got the pulse input. So we'll be drawing a graph as usual. And V in will be in blue and V out will be in green. And we need some values, and the values are 4.7 nanofarads for C, R1 is 10k, the voltage source is 5 volts, R2 is 10k, and that's it. So we'll label R1 and R2 as well. R1 and R2. So we've got the circuit labelled up. And we can draw out the input pulse as well. When the circuit's been off for a long time, when the circuit's been on for a long time but there's no pulse, this 5 volt source will charge up this capacitor through R1, so a current will flow up there and it will make this plate more positive than the other plate by 5 volts, so we'll end up with 5 volts across there, and this will be at 5 volts. That's okay. All we've got to remember is that our usual situation where there's no output before the pulse, well, this time there is. What is more, when the pulse goes through, because this is essentially a high pass construction, when we move this from 0 to 10 volts, we'll be moving the other side from 0 to 10 volts as well, because we can't charge or discharge this capacitor instantly. So this will actually go from 5 up 10 volts to 15 volts. So we'll have a step up here like this, up to 15. And then over the period of the pulse duration, that will decay down to some extent. Well, we don't know quite how much yet. We need to work out the time constant, and the time constant of the decay will be down to R1 to some degree, and possibly down to D1, except that this is 0 and this is plus 15 at the very extent of it. So that means that this is the direction of the current, voltage across the diode. So the diode is actually reverse biased, and the diode doesn't have anything to do with this. So at the moment, it's just a time constant here which is 4.7 nanofarads and 10 kiloohms. So that's 4.7 nanofarads and 10 kiloohms. So that's 47 microseconds. And then only trouble is, this pulse is only 100 microseconds long. So 47 microseconds, we've only done about 2 time constants, which is insufficient to get us back to our aiming voltage, which is 5 volts. Or to get us back to our starting voltage, if you like, or to reach the aiming voltage. So we need to know what this point is, and we'll call it Vx. Vx is equal to Va e to the minus t upon tau plus 5. Plus 5 is our offset, and Va is our aiming voltage, or the voltage difference across the exponential is falling through. So we've got Vx is equal to 15 minus 5, which is 10, e to the minus t upon tau plus 5. So we'll insert some numbers, and we'll have, that's 10 obviously, e to the minus, and we're at 100 microseconds, but we've got 47 microseconds as a time constant. And then it's plus 5, 6.191 volts. So we can say that Vx is 6.191 volts. Okay, so I'll get rid of this lot now. So I'm going to say, oh, okay, we're at 6.19 volts and the pulse has come to an end, so we can take that away, and that away, and that, and that, and that. And we've managed to keep 6.191 volts up here, and this is now going from 10 down to 0. So that means we have to have a similarly sized transition from 10 down to 0 over here. The only thing is, we're at 6.19 volts, so we're going to have to go down by 10 volts to whatever that is, which is 10 minus, it's 3.80, 3.809 in fact. So this is minus 3.809 volts. Okay. And then there'll be some other things will happen in the circuit. So in that instance, this 6.19 will drop to minus 3.809, and something we can say immediately is, okay, well, some current will flow out of this 5 volts through this 10k to restore this capacitor towards 0 volts, or to restore the output towards 0 volts by charging up this plate with the capacitor. Fine. The other thing we can say is, well, if this is 0 and there's no current flowing in this diode, then this point should be 0. In which case there'll be a voltage across the diode of 3.809 volts, which means it will be forward biased. 0 is bigger than minus 3, so that's how the arrow takes that direction. So that means the diode is going to conduct. So that changes everything. So not only do we have current flowing through the 10k from the 5 volt source into the capacitor, we've got current flowing from the 0 volt through the other 10k R2 through the diode as well. So what we'll have is an exponential rising like that for a bit. But when we get to 0, something else will happen, because once we've managed to charge up this capacitor to the point where this is 0, well, this is 0 and this is 0, and the diode will stay, as long as there's current in R2, the diode will be conducting. But once we've got 0 there and 0 there, even though this diode doesn't drop any voltage, there's still now 0 across the resistor, so there can't be any current through. So the diode will switch off, and that will mean that this part of the circuit essentially disappears, and we're back down to just 10k from R1 and 4.7 nanofarads, so there'll be a different time constant in this region here. Wow, that's not a very good drawing of time constant. There we go, that's a bit better. So there's this discontinuity at the 0 point. And we can say that this time constant will be, we'll call it tau 2, shall we call this one tau 1. So tau 2 will be that and that in parallel, or those two in parallel with that one, so R1 and R2 in parallel, so it'll be 4.7 nanofarads times, well, it's 5k, because it's 10k in parallel to 10k, which is 5k. So that will give us half of 47, 23.5 microseconds for a time constant, because that's 10 to the 3 and that's 10 to the minus 9, so it'll end up being microseconds. And then we'll have yet another time constant here, which is tau 3, and that will be just the 10k and the 47 nano, so that will be 47 microseconds. Well, that's fairly involved, and the question's actually asking us, calculate the time for which VO is below 2.5 volts after the falling edge of the input pulse. So we're looking from here onwards, this is the falling edge, how much time does it spend below 2.5 volts? Well, 2.5 is just here. So we're interested in this time. So it's partly made up of this time, which I'll call T1, and a further time that I'll call T2. And we've got to work out what they are and then add them up. So we'll first of all say, okay, for this exponential here, it's aiming for 5 volts. Now, the fact that it doesn't make it there because it gets changed by the diode switching off, neither here nor there, this is still headed up here. Wow, that's terrible. It wants to do that. Doesn't get the opportunity, but that's what it wants to do towards the 5 volt. So what we've got is a 5 volt offset and a 23.5 microsecond time constant, and we've got a change in voltage from Vx down 10 volts. So we're going to do, but on the other hand we have minus 3.809, and the exponential is falling across from minus 3.809 up towards 5 volts. So we have in fact Vx minus 10 volts, which is the drop there. So that's our input voltage initial starting condition, and then minus 5, which is our across what we've dropped the exponential, e to the minus t upon tau plus 5, which is our offset. So all this stuff, so it's 6.191 minus 10 minus 5, what does that turn out to be? Quick, grab a calculator. So we've got 6.191 minus 10 is minus 3.809, so this is our starting point, minus 5, minus 8.809, so the distance from there to our aiming voltage is minus 8.809, and it's going from a lower voltage to a higher voltage. E to the minus t upon tau plus 5, which is our final offset. So then we need to get T1 out of this somehow. Sorry, all of this is VO, should we say. And we're heading for the situation where VO is 0, because that's the amount of time that we're interested in here. It's where it crosses the axis, because that's where this exponential becomes invalid and the new exponential, composed only of R1 and C1 and C takes over. So we've got essentially VO is 0, so I'm going to just bring the 5 across immediately. So I have minus 5, and then we can say is equal to minus 8.809 e to the minus t upon tau. And then I can divide through by the 8.809, which will give us minus 5 over minus 8.809 in brackets is equal to, I'm going to take logs, so ln of that value, and that will leave us with minus t over tau. So if I multiply through by tau, that will leave me with minus t. So if I multiply through by minus 1, that will leave me with just t. If that seems like I skipped too many steps there, go back and watch the solutions to prior questions from this sheet, and you'll see me do all the extra steps, but there's not a lot of board space remaining. So we can punch the numbers in there, and we need to remember that this is the time constant we're interested in. So we've got minus 5 over minus 8.809, and we can take logs of that, and then multiply by minus 23.5 microseconds. That gives us 13.308 microseconds. So that's the time T1. So this is, I won't write it up there because it's a bit crowded. But that's that's T1. So having got T1, we now need to worry about T2, which is a much more sort of simple affair. We only have to worry about the sort of more regular stuff. We've got VA is VA, and VA is 0 to 5 volts, so it's 0 minus 5 e to the minus t upon tau plus 5, because 5 is our offset. So then we have 2.5 equals minus 5 e to the minus t upon tau plus 5. So the 5 can come across and we'll have 2.5 minus 5, and then we can divide through by the other 5, this minus 5 here. Tell you what, I'll write it out. E to the minus t over tau, and then, oh sorry, there's minus 5 in there, isn't there? So we'll divide through by the minus 5, and then we'll take logs, and then that will get rid of the e, and then we'll multiply through by tau, and then we'll multiply through by minus 1, and that just leaves us with t. So plugging that all in, but this tau is now the 47 microseconds because we're in the T2 situation. So we have 2.5 minus 5 divided by minus 5, half, logarithm of half, minus 0.693, times minus 47 e minus 6, 3.25, or 32.57 microseconds. So that's T2. Is that all we got? Yeah, it is. Excellent. So then all we have to do is sum them up, because we want this length plus that length. So we've got time below the time it takes for the waveform to recover up to 2.5 volts is 32.57 plus 13.308, and that's it. That's all in microseconds. So that's a 2. 32.57 plus 13.308 is 45.4 878 microseconds. And that's how you kill that one. The only thing that really makes this taxing is figuring out when the diode will start or stop conducting halfway through this recovery. And once you've got the hang of that, it's figuring out what your aiming voltage and offsets are in the exponential equations to make sure you actually get the right numbers out. And that is the end of the tutorial sheet. Sorry, problem sheet.